Thanks to Bowlife for that nice introduction. I'm Tyler Collins. I'm going to be talking to you today about diagnosing waste on the national systems through user-facing portals that have been developed by the um, national analytics team. Like Bowlife said, my background is mostly computer science and kind of uh, not quite machine learning, but genetic algorithms and evolutionary computation, and lately a lot more neuroscience. So if you have any questions about those sorts of things, don't hesitate to ask. And in general, don't hesitate to post some questions in chat during this talk. I find it really helpful just to like direct myself about what I'm explaining well and what I should, repeat in a slightly different way. Okay, so let's go ahead and jump in to today's outline. I'm hoping to keep it around 30, 35 minutes. That way we can have some open questions right at the end of the talk. Any more complicated questions, I'll definitely direct you to our ticketing system where you'll be paired up with some sort of analyst in your field of study to help you out more directly. But as I kind of stated in the abstract for this talk, this is a kind of continuing series done by my colleague and good friend James Desjardins about just investigating wait times and different job properties on the national systems. Um, Specifically on wait times, I want to discuss what's fair versus what a user needs. We'd all like the cluster to behave like our own personal computer, but it's not. It's a shared resource, of course. Um, but what's an interesting problem is how to actually investigate these sorts of things, especially when they're behind a barrier of maybe an arcane command line tool or worse, Slurm's command line tools, and how to, diagnose those over time. Um, and the focus completely of today's talk, which will be that researchers often do not specify um, accurately enough their requirements on their job, which is increasingly increasing like their wait times substantially. Some people wait weeks when a job could run much, much sooner if you take the time to properly profile your job and see what wasted resources are occurring. Okay. So, like I said, the previous talks and assumptions previous talks rather, were given by my colleague James Desjardins, and these are the three main ones. They're roughly in order here. So there was visualizing job properties with a package that James and I developed together. Um, there's a continuation of that builds on looking at accounts as a population and what people are able to actually achieve and what you should be able to achieve as a researcher as a default account versus a rack allocation. And then a more recent one there in the bottom, which I think is definitely a must view if you haven't already. But we'll be building off of these talks. But we can definitely conclude is that wait times are frustrating for users and they're difficult to diagnose if you're just interacting with the cluster. Okay. So, an important note here also, these are all hosted on the SharkNet YouTube. There's dozens and dozens and dozens. I don't even know how many right now, but tons of videos about all sorts of different topics. I've done things on Python and Python. We've done talks on Julia. We've done talks on all sorts of file system things. So if you're interested, please go take a look. It's a really great resource. Okay, so from those talks, a couple of important definitions pop out that I wanted to just make sure we're all on the same page for before we go forward because we need a common understanding. Okay, so job shape, this is something that I kind of refer to as just your job attributes taken as a whole. So if you submit a job that's 16 cores, 4 gigabytes in 7 days, that's your job shape. So if I ask you what does your job shape look like, you should tell me what you're requesting. Okay. Billing is a combined metric that kind of tries to approximate your job shape into one number, boiled down. It typically, on our systems, it doesn't factor in days or like your time requests, but that's still a dimension of your job shape. Okay. And the important point here is a single core job that requests 125 gigs of RAM is not billed, one core. It is billed a fraction of the node that you are taking up in that case. All right. And if you want more about that, we can talk more about that at the end when we have our open question period, but there's also some really great documentation available on our wiki. Okay. Waste, this is pretty easy to understand, I think. If you ask for 7 days and you only use 1 hour, you've wasted, not wasted your time, but you've definitely not needed that. And you waited for the scheduler to open up a 7 day slot for you, say, and that takes longer. And now you've kind of wasted that. A more direct waste would be I want 125 gigs of RAM, and you run your entire program, it finishes, you get the correct output, you've only used 5 gigs of RAM. And we'll talk about how to diagnose that, but that's a typical thing of waste. An allocation, that's typically what group you belong to. So I belong to quite a few. I'm a staff member, so I have my own, and I have several that I'm contributing to as part of supporting some local researchers. It's typically named after your PI, and there's two types and a third corner case. The two types are the default and a rack account. Okay. If you have a rack account, you'll typically know your PI will tell you about it. The only difference, mostly the only difference, is that the targets on rack accounts are higher and they have assurances of target, an assurance of how much of the system that they get. Okay, and then this last one I kind of snuck here on the bottom of the slide, but it's very important, and it's priority. Okay, so how the scheduler decides the ordering of which jobs to execute next. I want you to like get rid of any sort of notion in your head that this is like an orderly line, like you're lining up at a bank or lining up for a roller coaster or anything like that. It is a much more complex structure than just some sort of linear line. Okay. And an important thing here that has gone into in the previous talks is you cannot bank priority. Okay. You will always be able to catch up, and we see this in all sorts of different user accounts. All right. You're able to catch up to what your target is, but you cannot take 6 months off and then come to us and say, well, I had 6 months, I wasn't doing anything. Can I have that 6 months back? It doesn't work like that. The systems are a shared resource. You're allowed to catch up to your throughput, but once you're at that throughput, the scheduler will typically hold you to that. Okay. All right, so I talked a little bit about the conclusions already from those previous talks, but we'll formally kind of state them here. Researchers are often experiencing wait times without knowing what is causing them. So it can be malformed job shapes. It could be things like uh, um, I've lost my place here. Malformed job shapes. It could be things like requesting way too many resources and anything like that. Okay. And this can be addressed by understanding your priority and where you're at. And this is actually what I was trying to recover there when I lost my train of thought. But you're not knowing, if your account is underserved or overserved. If you've submitted 1,000 jobs recently and they've all run, it's probably no longer your turn, right? It's somebody else's turn to take up those resources on our system. Okay. And these things can be addressed by better CLI tools or a better understanding of CLI tools like some of the Slurm things like SACT. But the talks also go over things like cluster stats, which allow you to see how many jobs there are roughly ahead of you in queue. Okay, and also there were some Python packages we talked about in some of the older things and notebooks that allow you to very, very much drill down on a lower level to what's going on in the account. But overall, I think the most important conclusion here is the strongest way to minimize wait times is to minimize waste. If you have a job that requests 16 cores and you're only using 4 in part of your execution, then request the 4 and you will see a dramatic decrease in wait times. Okay, so all of this being said, I'm kind of harping on that wait times are bad, but an important principle here is that wait times are normal in a fair system. The way that our scheduler is configured is that once you've submitted a whole bunch of jobs and you've run and you're over target, it's no longer your turn. You can still achieve more than your target. It is certainly possible, and we've seen it hundreds of times, but you will be less inclined to run resources when you're overserved. Okay. But this kind of leads to the question of what is an acceptable wait time? I often hesitate to give a formal answer for this because it depends entirely on your field of study. But If you need some sort of heuristic, I like to give this answer, which is that if you can rerun things in less than a week, you you should still try and minimize waste because waste is bad, but that's pretty quick. You typically only meet with your supervisor once a week, unless it's a very close-knit lab that like there's less people in. But in some of the larger labs that I'm a part of here at my university, it's a once a week kind of thing. So if you can redo your entire analysis between meetings, you're good to go. Okay, awesome. So I just wanted to point this out here, and I'll in my slides I have a the command for you to copy and paste once the slides are released. But I just wanted to show you that in here, and this is a big blob of text, that I too have jobs that time out, that fail, that out of memory, that wait, that I've canceled. So even an expert user like myself who submits tons and tons of jobs on different systems, it happens to me too. Okay. So where to find your wait times and how to look at them. Um, if you have jobs that have been submitted already, you can look at SQ. I'm sure you're familiar with that. One important command that you should probably get used to as you become more and more of an expert user is this sact command. This basically shows the account history for a given um, you could make it search an account. You can make it search a partition. My suggestion for this command as you learn how to use it is ChatGPT is actually really good at writing queries for sact and doing summaries. So feed your questions into there and try it out. But this particular one that I have in quotes here generated the previous figure. Okay. So if you're looking to calculate your actual wait times from this, what you could do is you could redirect that to a file, pass it to Excel, or view any of our previous talks for Python packages, and you can calculate those wait times. But I'm assuming you're here because you do have wait times and you're wanting to lower them. So we're going to start looking into waste now and actually how to tackle that. So um, I'm going to basically be pretending for the remainder of this that like we're dealing with a ticket and a case where a researcher has sent me a request of, hi, I'd like to minimize my wait times. Okay. So the first thing that I would do and something that you can do now is you can log into this portal here. So I will actually type the URL into chat, portal.alliancecan.ca. You should be able to log in there as a user and view on a particular system your account. So typically def, your PI name, or RRG, your PI's name, and go see a summary of your priority in the jobs that have been submitted over time. Okay. And what you'll be presented with is a whole bunch of different options over on the left side of your screen, I believe. And so I'll go over these quickly so that, if you log in there, you can select where you need to go. In the top left, self-explanatory, select the system. So it's what system you're submitting your jobs on. I submit a lot to Narval these days, so that's that. Start date, end date, depending on whatever you want to look at in particular. This should be the last 30 days is the default. Over on the top right is the actual Slurm account. So your user will be fixed in if you're logging in as a user. If you're a staff, I see a couple staff names in here. You'll have a slightly different Slurm account bubble here where you'll be able to type in a user's name. Okay. After that, the allocation information should populate with the account that you're looking at. If it's a default account, it'll tell you what the default target is on that particular system at the time. If it's a rack account, make sure it matches your allocation. Okay. And then, depending on what type of job you're looking at, you should either switch this to CPU equivalent for CPU jobs or GPU equivalent for GPU jobs. Okay. That just changes the y-axis to actually match the billing of the jobs that you've submitted. Okay. So when we do that, we're typically presented with a graph like this. And what I would like to do is propose that this is a regular healthy account. They are seeing a day or two of wait time. They're seeing throughput. They're churning. So let's explain this figure. So on the y-axis, we have some units of use. I've taken a lot of information off of these figures because they are real users, but we're just trying to make it anonymous. So we have y-axis usage of some sort, and on the x-axis we have time. Okay. And these red dots are samples of the target. So that's roughly what you are trying to adhere, what the scheduler is trying to make you adhere to is that target. The blue bars are jobs by one user. So you can see these are actually fairly large jobs by one metric or another. Um, and the gray bars are queued resources. So what we can see from this figure is that this user is queuing up some jobs, waiting a couple days, a big burst of jobs go through, then it takes a little while for their priority to recover while there are more jobs queued. Okay, the jobs run and it's cyclical like that. They're getting the churn um, through their queue. Everything is slowly starting to run. Okay. This is a regular healthy account. If you're seeing usage like this, you should be fairly happy. If you're not, of course, take it to us and we'll discuss what we can do better. And we'll talk about that, of course, when we're diagnosing the waste. But on average, I would say this is a healthy account. This is something that looks like an underserved account. Okay. So at the time, if we look over on the left, you can see that they submitted 50,000 units worth of work. Unsurprisingly, this is cores. I could have left the y-axis labeled like that. We do not have 50,000 GPUs. But what we can see is that their usage, which is all the way down, squished on the bottom, definitely does not quite match all of the work that was queued up. And this can be as a result of jobs being canceled or anything like that. But definitely in the early parts of July here, where I've taken this sample figure from, the account was being underserved right over here. I hope you can see my mouse over on the left after the July 21st there. So that's roughly what an underserved account would look like. If your account looks like this, take it to us, or of course, we start talking about waste. If you're part of a larger group um, with a whole bunch of different workloads, this is an example of an overserved account. We have our gray bars that are showing queued resources. There's a whole bunch. We're roughly kind of meeting that red dot target. Over on the right here, we can see a wait time where there's a whole bunch of queued resources by to the left of August 11th here. And, it's kind of to be expected because there's an overage of target to the left of that. All right. That can be kind of difficult to see, but there's a way in the portal there. One of the options is to switch to a cumulative view. I think it's called running total. And what you can see is that this account is very, very well served. They're achieving their target and more. Okay. So we'll talk about what this case means in a second, but an important note here is the different colors are different users. So we have one user who's practically saturating this entire allocation. Maybe that's okay, maybe it's not, but that's something for you within your research group to figure out. All right, so there are three conclusions from these figures that you should draw on your own particular work, okay? Two main ones and one kind of hidden corner case. That is more of a social issue than than anything. Number one, if your account is not at its target allocation and experiencing wait times, so often the problem with this is you need to look at your job shape. Either you're requesting way too many resources, something like I'm asking for 20 GPUs when you really don't need 20 GPUs, or asking for 7 days when really most of the time it finishes in 3. These sorts of things will significantly increase your wait time. Okay. Now, the second case is a little bit more interesting, which is the account is over its allocation and is experiencing wait times. So this is a natural consequence of, you know, you need to fit more work into what you are submitting. So constantly your jobs being submitted with 16 cores when you only need 8, you could maybe pack twice as many jobs into your account then if you were to reduce that down. Okay. So 80% of the time, this is a classic 80-20 that I'm just generalizing with. This is fixable with better job shape parameters in the case of, like I'm just saying, talking about cores, reducing that down to what you actually need. The other 20% of the time, life is complicated and you definitely should send us a ticket and we can work with you on profiling and maybe actually changing your code base in some more extreme cases. Okay. The third hidden corner case is best illustrated by this figure. And it is that Slurm, the scheduler, does not actually see users within an account. Okay. It only sees the account as a whole. So let's say we take this figure, for example. I would assume from this, and I'm probably safe to assume, that the user in blue, who represents the blue color here, is submitting jobs that are much easier to schedule. And the other people who are submitting jobs are submitting larger jobs. So Slurm looks at the account and goes, okay, it's your turn. What do you have for me? It will often take the easiest to schedule jobs from that account. Okay, so you sometimes are competing against the other people in your lab in there. If you're seeing that, and that's the case, this is why I alluded to earlier, it's a social issue. You can chat with your supervisor, you can chat with that actual student, be like, hey, what can we do? You could also improve your own jobs, which, leads us to dealing with wasted resources again. Um, or you can consider exploring using one of the other national systems if they're both on the same system, okay? But this problem is a corner case. Okay, so concluding that previous slide, unsurprisingly, and the theme of the talk, we want to actually eliminate waste in both cases, even if we're waiting a whole bunch um, and we're underserved, or we're waiting a whole bunch and we're overserved, or even that corner case, right? We want to make our jobs as appealing to the scheduler as possible, and that means smaller jobs that are more accurate for what we actually need. Okay, so let's talk low-hanging fruit. Okay, so this is if you want to just like do the absolute bare minimum and just log onto the cluster and see, this is what I suggest. And everyone should be doing this, okay? Even me, which I'll talk about in a second here. Number one, probably the most important, actually look at the run times and provide a more accurate estimate. Um, if you know that your jobs finish in 3 hours 95% of the time, right? And you have a couple, say you're running some sort of optimization code that take a little longer. I would submit them all at 3 hours and resubmit the other ones and the chance that they fail, as opposed to submitting 8 hours for every job or 24 hours for every job and being certain. Okay. It's going to minimize the amount of time you wait in the queue. The best case is that you implement something like checkpointing and you can just resubmit those jobs, um, picking up where they left off, but I understand that's sometimes difficult and not always possible. But something you can also definitely do right now is you can go onto the cluster where you're submitting your jobs and you can run this utility Ceph. What it will do, you'll give it a job ID, is it will provide you a breakdown of what your job did. So I have this job here that I actually submitted. I don't remember quite what it was for. I believe it was for like a greedy best first type of optimization problem. So what we can see here, I asked for 4 cores. Great. I didn't really use all of the wall time. Okay. Sometimes that's problematic. But I only used 2 GB, maximally 2 GB out of the 10 requested. Now, I didn't particularly wait long for this job, so that was okay. But if we multiply those numbers by 10, you are definitely going to see wait times. So I strongly encourage you to do this, even if you do nothing else that I've told you today, from the portals, exploring your priority, or the actual usage portals we'll get to in a second. Try running Ceph on your jobs and seeing if you actually need the memory and wall time that you're using. Okay. And so again, I'm being honest with myself. This is me looking at my elapsed jobs, how long they've run versus the time limit. 6 hours, I actually used 3. 6 hours, I used 4.5. That's better. So on and so forth. These are bad in the middle. I've requested 8 hours, took 47 minutes. If I was running these tests at scale, I would definitely be seeing large wait times. Okay. Oops, I've skipped ahead. So run Ceph, even on another monitor if you have one right now while you're listening to me ramble about these wait times. Okay. So importantly though, Ceph isn't always 100% accurate and can be confused by multi-node jobs, strange memory allocation patterns, all sorts of things. Okay. So For a long time, this was a difficult problem, but now we have the user portal. Okay, so this is primarily developed by my friend Simone over at Calcul Quebec and is primarily deployed for the Narval and Beluga systems. There's a reduced development version available on Gram that is linked from within the portal, which I'll take a look at in a second, where you'll be able to do these, like look at your jobs as well. Um, Fear not. Even I believe Niagara has something similar, and Cedar has some of these things, but any principles you learn while debugging or investigating your jobs on these portals will generalize to all systems, including even your local one. Okay. It's powered by Prometheus and Thanos. Okay, Eric there just linked it. Excellent. So there's the link for the Niagara system one. I wasn't familiar. Thank you. So it leverages Prometheus and Thanos to report metrics from different sources. So we have exporters, which is the Prometheus kind of nomenclature for something that reports the status of what's going on. We have it on the compute nodes, login nodes, file system resources, all sorts of different things. So you can see what every resource is doing. The temporal resolution for this is very high, which is often a problem with Ceph. The sampling isn't great. The sampling for Prometheus and the things we're doing here is much higher resolution, so you can catch errors a little bit quicker. Okay, and what we're going to do is see what these jobs are doing at a lower level, and I will introduce one of my own personal stories in a little bit as well. Okay, so this is something that Simone has modified, but it basically describes for some of the staff people here, as well as some users who are interested, kind of how this all glues together. And essentially, we have our web portal, which is in Django, and it's pulling from Thanos, and that is basically something that lives on top of Prometheus, which allows us to aggregate metrics. If you're a user, don't worry. It basically just means you don't just have up-to-date information, you also have historical information on jobs, okay? I have jobs from several months ago that are existing in there. Okay, great. If you're interested in deploying this for your own systems or your own things, or just learning more about it and seeing how Simone has achieved this, the code base can be found on GitHub. Simone's always pretty responsive, so if you maybe open an issue there, or if you're a staff member, DM him on Slack, you're good to go. Okay. Awesome. So I'm gonna just switch tabs over here and have a look and show you exactly what's going on the portal. So once you log in with your CCDB credentials. We have this page in front of us. I have a staff page, so it looks a little bit different. If you're a staff member, you're able to go to URLs and search things. As a user, you're locked down to just your user groups, which of course makes sense. But what we can do here is we can look at the login nodes in the last hour, and we can see roughly what the load is once the figures have returned. Okay, we can see that they're definitely a little bit more under load. I was, of course, working on my slides last night in the middle of the night, and this was much lower. Okay, we can see the network. We can see that there's definitely a whole bunch of downloading going on. Okay, so if you're seeing problems with the login node, you can confirm what's going on through this portal. You can look at the actual file system performance of, I believe, 567. I think it's Home Scratch Project. I can't remember how it's named on this system in particular, but maybe somebody from Calco Quebec could post that in chat. But what I'd like to do now is look at actually one of my personal jobs that I submitted last week, helping out a user. So if I go to my user summary page, which I'm going to do this in the slides, and we'll look at the actual portal page as a summary in a second. What I'm given is project quotas. So I'm given my inodes, how many files I have. I'm given the amount of storage I have. So here's several data sets that I'm working on with researchers with. And I'm also given an at-a-glance summary of all my jobs. Okay, so this is already particularly helpful, where I can see the ask time and the use time. It's calculated for you, the submit, start, and end time. I have the job names. I'm pretty bad at naming my job names. I just have job.sh because it's a template I use to submit things. But you can also click more details on this portal, and what you'll be able to see is all of your kind of legacy jobs there. So I have a couple hundred that I've submitted on Narval. in the last little bit, and so those would pop up. But what I want to do is specifically look at the out of memory job, because this is something, as you can see, I was working on I guess 2 weeks ago now. Time flies. Um, and open up that job. So you can do that by clicking on the job ID. Okay. So when I click on the job ID, I'm presented with a whole bunch of different summaries. And right at the top, it gives me a whole bunch of warnings. Okay. Um, they're very self-explanatory. So less than one core was used on average, but four were asked for. Okay, that's something to investigate. Half the CPU cycles were used. Investigate. Out of memory, increased memory and asked and retry for this job. That's a good suggestion in general. And it's also complaining about threads. So this is helpful and already guides us where to look for your jobs. Okay, so after that, further down, there'll be a tabular summary. So you can look at, which cores you got on which system. I had actually asked for 100 gigabytes of memory and 4 cores. I didn't end up using all of that. We'll talk about that in just a second. And you can see it ran it in about 3 minutes. This was in the middle of the night for a quick thing, so don't always expect to see 3 minutes for 100 gigabytes. Okay, so the first thing when you scroll down for this job for me, I see, and maybe you'll see something similar, is this graph, which is showing the CPU cycles. Okay, and it's fixed exactly at 1. I requested 4, and I'm using 1. In this particular case, it's not an egregious amount of waste, but if you scale this up to you're asking for 64 cores and you're using 1, you're wasting a lot of resources. You're leaving a lot of things on the table. Okay. This is indicative, I can tell you, of a MATLAB problem where in my job script, I forgot to signal to MATLAB I was doing things in a batch context. That's my own fault, but that's where this comes from. But look for this in your own jobs. Look for things being pinned to that roughly 1 core limit because it's probably a configuration that you've done wrong in your software or in your own parameter selection. Okay. The next thing that it was showing was the memory, which was very interesting to me that my memory exactly grew in a linear fashion all the way up to the maximum allocated memory. Okay, this was very strange to me. Um, I mean, it can happen, but this was not what I understood to be happening from the code that I was running. I did submit with more memory, but I didn't let it finish because also on that portal, further down, what I was able to notice was that there was some weird file system things where I was writing files every couple of seconds. Okay. And that actually led me to believe that there was a huge memory leak in the program. Sure enough, there was, and I solved it. And now it runs in a fraction of the time with about 2 gigabytes of memory. Okay. So I can actually show live, this is what we have here. I can look at a complete interactive job. You will be able to do the same. Interactive jobs are supported. Okay, maybe there's more people logging in. Okay, so I had 16 cores. I barely used anything. Not my greatest. 32 cores, also barely using anything, but I believe I was trying to debug a particular software package and verifying that it was working. Okay, here's the actual job. That I was showing in the slides. You can see that I did have MATLAB not properly exactly configured for running in batch mode. All my summaries are here. Same figures I was showing you. It also shows you the threads, common MATLAB issues, Ethernet, InfiniBand. All of this stuff will be available for you to look at for your own jobs. Okay, I believe there's also one other maybe interesting job we could look at here that is something I've worked with before. Let's just wait for it to load here. Might be a little slow with everyone logging in. Okay, we'll just move on really quickly and I'll keep an eye on it in the top there. Okay, so one of the things I promised in this talk was showing you what different waste patterns actually look like. Okay, so these next couple cases are not myself personally, but are actual real handpicked legacy cases where a user has complained about a wait time and I went and looked at their things in the portal and I was able to find a whole bunch of waste and significantly decrease their wait times. Okay. So unsurprisingly, the outcome of all of these was to reformat their job shape and resubmit, and things were much better from there. Okay, here is a real one. This is a real user. It's not even a special case. It's happened before. This user has approximately 1,536 cores actively allocated overall, and on average, they're using 20. Also, their memory ask is roughly 3 terabytes total, and they're using 200 gigabytes. Okay, so this is a slightly different summary. It's actually where you're looking, my page is loaded here. It's actually your user summary page. Okay, so that's what I'm taking a screenshot of from a particular user. Okay. On average, they were seeing 24-hour waits per job, contacting them, dealing with these jobs. Their jobs basically are running in about an hour now. Okay. But looking at the portal, diagnosing that all of the things they were asking for, every job that they submitted with was leaving tons and tons of cores on the table. That wasn't affecting their execution at all. It wasn't speeding things up. They were basically just dead resources sitting there in the water, contacting the user and dealing with it. Significantly less wait times now. Okay. Another one here. This is a more interesting one and something that the user portal is really, really, really great at helping with. This was a job that was an approximate 3-day wait. I've taken a snapshot of the beginning of the execution, but whatever algorithm they were running, it seems like it was highly parallel in the first couple of iterations, but swiftly fell off. Okay, so this becomes really, really excellent as a talking point, because you can see that, okay, maybe the execution would be faster if I request 64 cores, but is that worth waiting the 3 days when it really kind of falls off to only needing 8 cores after the first 3 iterations? And that's something that you'll definitely be able to explore with the user portal as well. Okay, an 8-core job is going to wait significantly less than a whole node job in general. Okay. Here's another one. Over a week of waiting for this because they were asking for practically a terabyte in memory on a small core request. Looking at the actual job, what was actually necessary is 3.8 gigabytes. I assume that the user was receiving correct results from their job, as they never complained about that. But these kind of requests where you're guessing and not actually looking are what contribute to the largest amounts of wait times. Okay, this is a spicy one, I would say. I don't really have a great way of measuring how much waiting was being done per week, because there were so many jobs, but definitely hundreds of hours of queue time per week for this user. You'll also be able to see roughly how much of the GPU you're leaving on the table, how much GPU waste there is. Okay, and there is a whole bunch from this user. I'm not sure if what was happening was they, had a bug in their torch code or what was going on, but they emailed us asking about wait times. We got back to them saying that, well, you could try resubmitting with less or figuring out what's going on with your own software code, and they were able to significantly reduce their waiting time as well. Okay. But this platform isn't just good for, finding out where things are wasting resources, but it also really helps with debugging. In that previous case that I was showing where it was severely multi-core or multi-GPU, it'll help you debug those. Interactive jobs are supported, as you saw, so you could submit an interactive job, go there, run some of your code and follow it along. It is high availability like that. You'll be able to see it right away after you refresh the page. You can filter the jobs by state, so you can look for your out-of-memory jobs. The InfiniBand exporters are on there, so you can look at that information. And maybe if we do have time on another monitor, not on my main monitor here, we could look at if users have any jobs they would want. We could look at something like that if we have time. But the takeaways here is that eliminating waste via job shape optimization is the best way to reduce wait times. There's the low-hanging fruit of Ceph. There's investigating your priority through the first portal that we looked at, so you know why roughly this is happening. And that's a complete historical picture of usage for your account. Okay. Then you can move on to the user portal to eliminate waste. And that's, exactly what your jobs are doing. So you have a very accurate idea of how many cores you actually need, how much memory you actually need. And really, that I'm hoping through all of this, the users here are seeing that this is easier than it's ever been before to actually get up-to-date information about what your jobs are doing and what your account has been up to. And from there, hopefully having a better experience using our services. So that's everything for the planned talk now. Thank you very much, everyone. Balai, do you want to stop the recording and maybe I can take some questions now from chat or otherwise?